Hello everybody, good afternoon or evening or morning, depending where you are. Today I'm very happy to have Arthur Choplin with us. I was curious to learn more about intermediate neutron capture process, and I think that this is a great opportunity for learning a bit more about that. And Arthur did his PhD in Geneva in Switzerland, and then he did his first postdoc in Japan at the Konan University, and now he is from 2020. He is a postdoc in Bruxelles at the University of Bruxelles. So thank you, Arthur, and enjoy your talk.
So thank you very much, Marta. Thank you, and thanks to you and Anna and the organizers of these seminars for organizing this and inviting me. And I'm very glad to say discuss for maybe 40-45 minutes the I process, the intermediate neutron capture process. I will try to spend roughly 15 minutes roughly on each of these three parts. I will try to give a kind of overview of the I process, but also it's difficult to not mention some other processes which are related to this one, especially the slow, the S, and the rapid R neutron capture processes. Maybe you know that, or we will discuss a little bit that as well. Discuss some specific stars which are called AGB stars, in which the I process can develop, also the S, and also a bit more about the I process. So I think it's not something new for you. I think one of the big goals of nuclear astrophysics is to understand how we can have gone from there to there, like the periodic table just after the Big Bang with very few elements, and then many more elements today. The idea is to, I think, understand how, where, and when were these elements synthesized. So how, by which processes, like stellar fusion, neutron capture, where, in which sites, massive stars, neutron star merger, whatever, and when, at which stage of the universe. I mean, just after the Big Bang, or maybe much later. And to address these questions, I think we have to, rely on different fields, I would say, which are connected between them. Observations, of course, but nuclear physics, both from experiment and theory, do some astrophysical site modeling, and also galactic chemical evolution modeling. So in Brussels, I think, are working on three of these aspects: nuclear theory, astrophysical site modeling. I'm part of this team, I would say, and also some observation. So this is not very up to date. So I would need to update this slide, but yeah, this is roughly what we do here in Brussels related to this topic, so related to nuclear astrophysics. So going back to this plot, there is a very important class of process, which are the neutron capture processes, and we know that they synthesize almost all the heavy trans-iron elements in the universe. This is really what we think. And one of these process, I will start with that, is the slow neutron capture process, which operates at a time scale of typically 10 to the 4 years, roughly. At low neutron density, and here you have like a part of the nuclear chart, and you can see if you start from a typically a nuclei like iron, like a big seed, you start to capture a neutron, and at some point you reach an unstable isotopes, and you beta decay, and then capture a neutron, and you follow like that path. And in this case, we can call that the S process path, which really sticks to the value of stability. These black squares are stable isotopes. And if you go at the other extreme, you have the R process at typically 10 to the 25 neutron per cubic centimeter. So this is here, maybe it's not indicated, but like the unit of that is neutron per cubic centimeter. So 10 to the 25 is a lot. And with as much neutrons, you can go very right and follow another path, which is the R process path. And then you have the I process, which is just intermediate between the S and the R process in terms of neutron density, in terms of time scale, and also you have like a path which is intermediate between the S and R. So this is, yeah, just the very first thing I wanted to say. And of course, each of these processes will leave a distinct chemical fingerprint. What about the sites? So where, for instance, the S and R process can take place in the universe. So for the S process, it was recognized that the S process can develop in specific stars, which are called asymptotic giant branch. And I will discuss that in more details later. There are many references about that. I put a few. And also the S process can develop in massive stars during the core helium burning phase, and also during late stages, especially in the shell carbon burning of these massive stars. The R process, you need a more extreme environment. It can be neutron star mergers or peculiar supernovae, like for instance collapsars or magnetorotational supernovae. But the neutron star merger is, I think, one big scenario, I think, candidate for our process. But yeah, might not be the only one. What about the I process? So this is a bit the cooking recipe first of the I process. So the I process, and this is a quite general definition, the I process can happen when hydrogen is mixed into a convective helium burning zone. So you take a pan, you have helium inside, you make it boil, so it's burning, and you put some hydrogen inside, and you have I process. And we have what we call in here like a proton ingestion or hydrogen ingestion. This is quite general. And so if you take a star, it is a very schematic picture of a star with the core, helium shell, hydrogen shell, and envelope. You just need some kind of interaction between the helium shell in purple, I would say, and the hydrogen shell. You need like kind of mixing between these two regions. And so in order to have some, I would say, ingestion of hydrogen material into deeper layers, into helium shells. We will discuss that later again. But maybe you can remember first that there is like a strong link between proton ingestion and I process. So if you have a proton ingestion, you should have I process. And these are, I try to be a bit more exhaustive for the I process because it's the topic of today. These are the possible sites that were recognized for hosting proton ingestions or I process. And it includes AGB stars, accreting white dwarfs, massive stars during the very last living stages, something that we call core helium flash. So some stars can experience core helium flash at especially low metallicity, and this was shown to be a possible site for I process as well, and also post-AGB stars. So I will not go into the details of all these sites because first I don't know all the details, and also I don't have time, but I will really discuss the first site, which is very much discussed, I think, the AGB stars, also a little bit of maybe accreting white dwarfs. And also, again, you can remember that something which is common in all these sites, these 5 sites, is that the I process is developing after like a proton ingestion. So after this kind of, mixing of hydrogen into some helium burning zone, convective helium burning zone. Okay. Yeah, and here I just highlighted the works, the models, I would say, that include like a big network in order to really follow the I process nucleosynthesis with like all the elements and up to lead and heavier elements. So yeah, there are not a lot of works really dealing with the heavy elements nucleosynthesis induced by this proton ingestion, so the I process. But there are some. But still, even if there are not so much work, you can see here, this is I want you also to show you maybe that the I process is not a completely obscure and weird topic by showing that since quite recently, since the year 2010 something, there is a much and more publications about the I process. And this plot is just showing you the number of publications as a function of year for the IS and R process. And you see that, of course, I process is not as much discussed as the other processes, the slow and the rapid neutron capture processes, but still, it's not. It's growing, I would say, and it's also quite recent compared to S and R process. But actually not so recent And also I think it's nice to remember that the first time the I process was mentioned in the literature in papers was back in the 70s in these two papers by Starfield, Truran and Sparks and Cowan and Rose. But then this topic was not getting a lot of attention, and later on, because of some reasons, people tried to they get back on this topic and try to investigate a bit more this I process. So now I would like to spend some time on observational motivation. So, or I would maybe I could have called that evidence, observational evidence of I process. So why would we need I process? So can we see some I process happening in the universe somewhere? So first of all, I would like to remember that the sun, if you look at the sun, you look at an integration of many previous events. So you have a very schematic view here of the galactic chemical evolution from the first star to the sun, and the sun is formed out of a material that was enriched by many previous supernovae, stars, the neutron star major, etc. And of course, you can learn a lot with the chemical composition of the sun, but you know, it's like an accumulation of many previous events. For instance, in the sun, these peaks here, I will not go into detail here, but these peaks around xenon, barium, and lead, etc., can be very well explained by the S and R processes. So this is a kind of strong evidence of S and R, of the existence of S and R processes in nature. By contrast, if you look at metal-poor stars, it's quite interesting because these metal-poor stars, they formed quite early in the universe, and because they you know, at the beginning there were no metals. So if you look at a metal-poor star, it formed probably with one or a very few previous events. And then in these metal-poor stars, we can really see probably individual nucleosynthetic processes and not an accumulation of many, you know, S and I and R process, etc. Maybe we can try to identify these individual processes. So this is a metal-poor star here, and here is like a S process star. So you would see here the dots are observations. This y-axis show the abundances, so the amount of each element relative to the sun in log scale. And the line is showing you an S process model, an AGB star in this case. And this was just to show you that there are some stars other than the sun that are really showing an S process composition, you know, like, and that can be very well explained by S process models. And this is the same for R process. There are stars like this one that can be relatively well explained by R process models. So in the orange line, for instance, is showing you the yields of neutron star merger models. Yeah, and then some stars have a surface chemical composition very much compatible with S or R process, but some don't. And here is one, for instance. I will like to focus on one example here to make it quite clear. Like this star, and this is just the heavy elements, but this star is a metal-poor star, and the red line is showing you the best fit we can obtain using an S process model. So you see that there are some problems. For instance, here around strontium, yttrium, zirconium, but also erbium, europium, there are something that doesn't work. And here is what you can get at best if you use an R process model. And I indicate here the chi-square, which is even higher in case of the R process model. So this is probably not a S star, probably not a R star. You see that there are some problems again with R process here. So why not maybe a mixture of S and R process? So this was quite like a simple, but can work actually, an idea, a simple idea, but this can work probably. Like you have probably this star might be like a mixture of R plus S, and we can check what we can do with that. And you have this green line. So this green line is just showing you what you can get at best by mixing, if you mix like an R and an S process model. So it's better. You can see the chi-square, which is about 3, but still there are some problems. And of course, you can understand where I'm coming now. This is an I-process model. So in this case, I will discuss that later in more details, but the black line is an AGB star that experienced I-process. And in this case, it can reasonably well reproduce the chemical composition of this star. So this is like, it was a bit busy. So I just put like the 2 best models here, and you can see the table summarizing the chi-squares. The I-process is clearly the best model here. And it was just to show you that there are some stars that cannot be explained by S and R processes, even a combination of 2 stars. And then we really think that I-process is a good solution, and it is a kind of, I don't know if I can say an evidence of I-process, but it's a strong indication that I-process is at work somewhere, you know, in the universe, I think. And this is like just, I showed you just 1 star. This is like a summary plot showing 14 of these I-process stars. And you see the x-axis is like the best chi-square you can get if you use an I-process model, an S-process model in black, or an R-process model in green, and an R plus S in blue. And you see that in most of the case, of course, not always, but the I-process is giving like the best solution. And this is a kind of indication that, yeah, again, the I-process it gives some credence, I would say, to the existence of the I-process. Okay, there are some other evidences, or I quote that because I'm not sure we can call that evidences, but some indications that I-process is operating in the universe. And this is just a list. I will not go through that, but also some you can find some possible signature of I-process in grains, prestellar grains, open clusters, or like stellar clusters in some special objects as well. Yeah, so I will go now to jump to the second part, and would like, I hope you, it was like, my aim here was really to try to convince you a little bit that, yeah, the I-process is like a process that can solve some problems, I would say. And yeah. So now I would like to discuss these stars, so these AGB stars a bit more in details. So there are some very good reviews on AGB stars. You can see it on the top right. I will say just a few things about AGB stars. This corresponds to the end life of stars between 1 and 8 solar mass. The time scale of this stage is about 10 to the 6 years, and during the AGB phase, there is a very complex interplay between nucleosynthesis and mixing, and also there are strong stellar outflows, strong stellar winds. So this is like a schematic view of an AGB star on the right. So the AGB star is the red star, like the big red star. And if you zoom, there is a big envelope in red. If you zoom in the center very much, you will see that there is like a carbon-oxygen core here. And it's like surrounded by an helium burning shell in blue and a hydrogen burning shell in yellow. Something which is quite interesting with these stars is like the presence of technetium in their spectra. So you see here on the right, like a star which is rich in technetium. So this is the spectrum of the star. And this is a star which is an AGB star which is poor in technetium. So there is a clear difference. And why technetium? Because technetium, it's quite interesting because it has not stable isotope. And the longest lived technetium isotope is about 10 to the 6 years, which is very small compared to the stellar lifetime of these objects. And then what does it mean? It means that this technetium has to be made really in the star now. So when you observe it, it cannot come from previous stars, from like, you know, ancient generation of massive stars or whatever. It really needs to be formed now in the star, really in the few past, I don't know, 1,000 of years or so. And this is a kind of really a proof that there is an ongoing heavy elements nucleosynthesis in AGB stars. And of course, how? So how can this AGB star synthesize elements in their, I would say, interior? and then maybe transport these elements from the interior to the surface. And then we can see this technetium and other elements like, I don't know, barium, strontium, lead, etc. So in order to answer this question, we need to construct stellar models. And of course, stars are 3D objects. So we want 3D models. And the thing which is, of course, 3D models are very good, but the thing is that with 3D models, and also 2D actually, only very small parts of the star's life or star scale can be modeled because it's computationally too much expensive. It is impossible to model the full stellar life and the full scale of the star in 3D. And this is the same for 2D actually. You can, of course, study very specific region in the star, or maybe a short amount of time you can look at the convection in the stars, whatever. But the only way to have the full life and scale of stars and also the full nucleosynthesis is to go 1D. And of course, the 1D models, maybe the most well-known 1D code, stellar evolution code, is MESA. Maybe you know this code well, or I don't know, but I listed a few codes here. The bad thing with 1D is that, of course, you have to assume spherical symmetry, and you also have to consider simplified theories for 3D processes like convection in stars. So in 1D, you divide your star in shells, typically thousands of shells. You solve the stellar structure equation, and you have to consider important ingredients like nuclear reactions, mixing, mass loss, opacities, etc. Equation of state. So it's already quite complex. It's not very easy to do some star in 1D, even in 1D. And the good thing, and this is, I think, why people use 1D codes as well, is that of course, they are wrong, the 1D codes, because stars are not 1D, but they are not completely wrong. And observations, they really, I think, confirm the general picture of stellar evolution predicted by 1D models. So, of course, it's not working perfectly, but yeah, I think it's not. I'm not the only one. We really think it's not completely, out of reality. Okay. So let's take a slice of an AGB star. So you recognize again the carbon-oxygen core, the helium burning shell, hydrogen burning shell, and the envelope. And when you go from 2D to 1D, you can look at this kind of diagram I'm looking at every day, which are called Kippenan diagram. It's a time evolution of the star. So the y-axis is the radius or mass coordinate of the star. So here you are close to the surface. Here you are close to the center of the star, and you see the time here. You see the carbon-oxygen core, the envelope, and these are these things, and in the middle are convective thermal pulses. These are kind of thermal instabilities of the helium shell that occur at regular intervals. So to give you an idea of the time scale, you have like a thermal pulse is lasting for about 100 years, and then you have this interpulse stage of 10 to the 4 years, roughly. And what I wanted just to show you, I will not go into details here because it's not the main topic, but these AGB stars, as I mentioned at the beginning, are a possible site for hosting the S process. And this red region here is really highlighting where this S process is operating in AGB stars, or in AGB models, I would say. So the idea is you have the convective envelope at some point that goes down, that there are some protons that mix here with carbon-12, and at some point you have some kind of what we call a C13 pocket, and this reaction here, C13 alpha N, will give the neutrons. So you will have C13 plus alpha, so plus helium-4 will give a neutron plus oxygen 16. And the typical temperature is 100 million Kelvin. Then this S process here material here in the star will be engulfed by the next thermal pulse. Here, like it's boiling, like the mixing is very fast in this thermal pulse. And this region of the star here will be enriched in S process elements. So I represented here in red. So this red region is rich in S process elements, and then the convective envelope at some point goes reach deeper layers and will take some of these S process elements because it will reach this red region, and then some of these S process elements will be dredged up to the surface. And the surface of the AGB stars will become enriched in technetium, in strontium, in barium, in lead. So this is how the S process is operating in AGB stars. And there is another kind of S process also that we call maybe convective S process that can take place as well at the bottom in AGB stars, but at the bottom of thermal pulse at higher temperature, and thanks to another reaction, which is neon 2012 fine. And it occurs mostly in massive AGB stars, which are hotter. So what about the I process? In some cases, this was shown by quite a long time ago, in the 60s already, by Schwarzschild and then by Japanese people, that in some cases, the entropy barrier, there is an entropy barrier here at the bottom of the hydrogen burning shell. This barrier can be surmounted by the energy released by this flash here, by this thermal pulse. And in this case, we will have a proton ingestion. And if you remember, like what I said at the beginning, when you have a proton ingestion, you have you can have an I process. So this is here like a schematic view of an AGB star with proton ingestion. So it is schematic, but still realistic, I think. So if we look at a real model, you will see something like that. So the first thing you see is that it's quite different from before. You see here, like it looks like that. And now if you have like a proton ingestion, it becomes like that. So the thing is that the structure of the star is really much modified by the nuclear energy released by some nuclear reactions. And this is why the aspect of the plot here is different, you know, when we have this proton ingestion. This proton ingestion is releasing a lot of energy that transforms the star, I would say, the internal structure of the star. So what's happening is that protons are going down. They are burnt very quickly by this C12 P gamma reaction. It gives some nitrogen 13 beta decay in C13 in about 10 minutes. And then at the bottom of this pulse here, there is the I process taking place at a temperature of 250 million Kelvin, roughly, still with this reaction, C13 alpha N, but at much higher temperature compared to the S process. And then this gray region here, this is the convective zones, and the mixing is very efficient. And then this I process material will be transported up to the surface. And the surface of the star will be also enriched in I process products. So, and then the AGB phase can resume with, you know, further standard thermal pulse with convective S process, with S process here, etc. So to summarize, there are three modes of production of heavy elements in AGB stars, two S process and one I process, I would say. With each time, I put here the main reaction, giving the neutrons, the typical temperature, and the resulting typical neutron density. So there is and the thing is that combinations are possible. It's not just this one or this one. You know, you can have I and S process in the same AGB star. And then this material, which is reaching the surface, is ejected through stellar winds. And I wanted to show you this picture, which is like, it's quite beautiful. It's like the ring nebula captured by JWST, the telescope. And what you see is like a dying AGB star. And in the center, you have like the central star, which is now a 0.6 solar mass star, a post-AGB star. So it's actually an AGB star that lost its envelope. And it will soon become a white dwarf. And this, the thing you see in red, reddish, yellowish colors are really the material ejected by the AGB stars. And this is this material that, you know, might be enriched in S process elements, in I process elements. Okay, so if we look now a bit more in details about the I process nucleosynthesis, so what's happening here, really in the model here, you know, at this in this small zone where the I process is going on, you know. So what's happening there? Okay, so this is like maybe the last part, and so if you look at the nucleosynthesis, really here, like at the bottom of this thermal pulse, so in the AGB model, when the I process is operating at its maximal neutron density, so you see here the neutron density is about 10 to the 15 neutron per cubic centimeter. You have here in red the mass fraction of all isotopes, and in red is the main I process path, which is not, you know, very far. It's not on the value of stability, but still not very, very, very far. So it's not really different from our process. But still you need to include like a lot of isotopes if you want to follow this high process nucleosynthesis, more than 1,000, and at least you need also 1,000 N-gamma reactions. Something I want to mention is that, of course, there are a lot of different references in order to take the reaction rates. Here we took like you know, some in order to compute these AGB models, we took the rates from various works like NACRE, StarLib, TALI, some N-gamma rates were computed theoretically with TALIS, and also NUBAS for the beta decay, etc. The thing which is here, I think, important to have in mind is that about 75% of these 1,000 N-gamma rates are only theoretical. So they are not experimentally constrained. And this is why to make this calculation, these high process calculations, we really need some nuclear physics input both from theory and experiments. And of course, we would like to have more, you know, experimental constraints on these N-gamma rates a bit far from the stability. This would improve increase the predictive power of these high process models. But of course, if you take like a N-gamma rate which is far from the value of stability, it's very difficult to get the, you know, the rate of this reaction. But here are a few works, recent works that managed to, thanks to a method which is called the Oslo method. So I'm really not an expert on that, but that is able to, you know, constrain experimentally some N-gamma rates a bit far from the value of stability. And in this work from Markova, it was about the tin isotopes. And then there was also a work by Artemis Pirou about the barium isotopes and also nickel, some nickel reactions, I would say, that would be constrained experimentally thanks to this method. So where does it end, like this high process path? So you can go up like this, and one question I can ask is, like, where does it stop? Actually, it can go quite high, and it can even go, you know, to the actinides region and to the super heavy elements where you might have at some point even fission and so on. So it was shown by in the 60s by, I think, Clayton, and that if you take like a slow neutron capture process, you will have a cycle in the lead bismuth polonium region, and you will cycle in this cyan area here. You will never be able to reach, you know, to bypass this region and to reach this uranium and thorium, for instance. Actually, while the neutron density is look, if you have a neutron density below this threshold value, which is 5 × 10⁻14 roughly, you have a cycle, this cycle here, and you cannot synthesize these very heavy elements. While if you go just above that, the cycle is broken and you can synthesize these thorium and uranium elements. And this is like a recent work that we did, like to show that indeed, like this high process, you know, can synthesize these very heavy elements as well. Not only the R process can, because like the neutron density is just above this threshold of 10⁻14 roughly. So to summarize, the S process ends around here. It was shown in the 60s by Clayton and Rosbach. The R process, of course, goes up. There is no, it goes very, very high, but also the I process. And it's often said that the actinides, they can be produced only by the R process during extreme events like neutron star mergers. But here I just show that it's also possible when the I process is operating in AGB stars, but also possibly in other sites. So the question also I wanted to address today was to show you at what stars are experiencing this proton ingestion, because I said proton ingestion may happen in AGB stars. But I mean, which stars, which mass, which metallicity? Does it happen in all stars, in all AGB stars, or not? So this question is important to address, for instance, for galactic chemical evolution. If you want to know, if I take like very low metallicity stars, do I have high process? Do we have proton ingestion? If I take solar metallicity stars, do I have high process or not? What is and if I take a 3 solar mass star, does I experience high process or not? So this is like what I'm trying to show you here with the plot showing the metallicity as a function of initial mass of the star. So you have the sun here on the top left. And this is like a compilation of different works, which are listed on the right. And each point represents an AGB model. And when it's red, it means that there is like a proton ingestion in this model. When it's empty, when it's white, there is no ingestion happening. And you see that everyone more or less agree, whatever the model, the stellar evolution code, whatever, that there is a zone here in gray, which is I would call it the ingestion zone or the high process zone, where you can have high process, and it's at low metallicity and at low mass. So the high process or hydrogen ingestion happens preferentially in low metallicity, low mass AGB stars. And the reason of that is, and this is like very, I mentioned that very quickly, but there was some work studying a bit that, is that the entropy barrier that I was mentioning earlier during the talk, the entropy barrier at the bottom of this hydrogen shell is a bit smaller and easier to cross at low metallicity and at low mass. Okay, but the thing is that this gray zone here may be bigger. It may be bigger if some extra mixing is included. And this is like the subject of a work we did recently. And just very simply, I will introduce the idea is that if you like consider like, again, this is a kind of very, very simple Kippenham diagram with the stellar radius here. So here we are close to the surface of the star, close to the center. And this is in gray, the thermal pulse with convection. This is like in green, the hydrogen-rich zone. And in this case, you can see that there is no connection between this thermal pulse and the hydrogen-rich zone. And then, therefore, there is no hydrogen ingestion, no proton ingestion, and then no high process. But what is very common to do in stellar models is to include some, extra mixing and especially overshoot. So overshoot is just something to try to better mimic convection, like what's happening in 3D. And it's just so you just extend the convective zone with some laws, exponential laws or whatever. You can constrain this red zone. Like the recipe can be, informed by 3D models or whatever. But the idea is to extend a little bit these convective zones, because it will not stop, the boundary of the convective zone is not sharp, and it will extend a little bit. And you see that if you include overshoot in this very simple schematic view, you will like connect the pulse with this green zone, and then you will have high process and hydrogen ingestion. And this question, we tried to look at that in a recent work, like how does this impact the occurrence of high process in AGB stars? So coming back to that, this is like all these models here are very standard models, I would say, without mixing. It's just simple, I would say, models with simple AGB stars, no rotation, no overshoot, no etc. But if you include a little bit of overshoot, which is like the strength of the overshoot is controlled by this parameter here, f top, whatever the value, but just if you put it at 0, you have something in gray. If you put a little bit of overshoot, you see that the zone here, the high process zone, will be extended. It extends with the strength of overshoot. And if you increase the strength of overshoot again, you will have the ingestion zone will extend toward this blue line. And if you increase again this f-top value, you will have something like that. So this was to show that the yeah, just the ingestion zone, the high process zone can be bigger. So if you just have this, then the high process in the universe will happen just in these stars. But if you include, some mixing, you see that this star, which is almost a solar metallicity star, or also more massive stars, will also experience this proton ingestion and then high process. And the problem is that we don't know what is the right zone, because we don't know what is the value of f-top. Yeah, we need for that maybe to get some constraints from 3D models, or yeah. But this is difficult now to say what is the right zone, I would say. So yeah. Going back to the nucleosynthesis, this is how the nucleosynthesis look like after an high process event, so after a proton ingestion. So what you see here, again, the y-axis is the abundances relative to the sun in log scale. And these are, I just took one model, which is a one solar mass star at low metallicity. And here, the lines is showing you the chemical composition at the surface of the AGB star after it has experienced this, proton ingestion and high process. And you see that the surface become enriched in, so I mean, before this event, before the high process, it would be like a flat line, so nothing at the surface. And after, you see that there are some elements like barium, europium, lead, which are enriched a lot, which are enhanced a lot at the surface of the AGB because of the high process, and also thorium and uranium. And this is also just to mention a little bit briefly the nuclear uncertainties, because of course, as I mentioned before, there are many rates and gamma rates which are theoretical, and then you can have of course, many uncertainties linked to nuclear physics uncertainties, I would say. And here, this is what we try to do in this recent work by Sébastien Martinet. Try to look at what is the impact of nuclear physics uncertainties on the yields on the high process nucleosynthesis in AGB stars, I would say. And so very quickly, like here is just kind of summary of that, and you can see that for each element you have many dots, and actually these are for each element there are 50 dots, because we did like 50 models with 50 different sets of n gamma rates. And these blue and red lines are showing you roughly the nuclear uncertainties that we obtained with this method, which is described in details in the Martinez paper. I'm not really aware of all the details, so you can check if you want like to know more about that. But you can see that the uncertainties roughly they stay in the range 0.5 1 dex. You can see on the bottom plot. This is like the difference between the blue and the red lines. But the thing is that if you look at the thorium and uranium, the uncertainties, nuclear uncertainties, becomes huge. So yeah, this is also a big question. So it might be that it might be that actually thorium and uranium production in AGB stars would be very small, by the high process. If you have because yeah, it can be very small or very high. So this for that we would need experimental constraints. Yeah, from the nuclear physics community, probably. So I'm almost done. Probably I will stop soon. These are the yields. I wanted just to show you the yields of 4 elements. These are each dot, all dots represent AGB models at different metallicities. And this is strontium, barium, europium, and lead. And the different symbols are different masses, initial masses, from 1 to 3 solar mass. And so there are different things to say about these plots, but maybe the most one of the big feature here is to see that the high process production is decreasing at high metallicity. So if you increase metallicity, you see that at some point like this strontium over iron goes to 0, and also barium and lead. So it means that there is no no net production of strontium, no production of barium at high metallicity, even if these models are experiencing proton ingestion. And this is because when you go to high metallicity, you have more iron, so you have more seeds. The iron are the seeds that will capture the neutrons, but the amount of neutron will stay the same. And then if you have too much iron, to make it simple, the iron will take all the neutrons. And then you will not be able to go very far. You will not be able to transform this iron into lead, into barium, etc. You will just end with elements around iron. I would say to make it simple, the iron will take all the neutrons. And this is why there is no enrichment in strontium and barium, etc., when this ratio here, the metallicity, is high. These are, to my knowledge, the only publicly available high process yields. They are also from the group of Pavel Denisenkov, Volker Wig, that work quite a lot on the high process as well, in massive stars, in AGB stars, maybe, and also in accreting white dwarfs. And maybe just to show you a very quick comparison between these two possible high process sites, so accreting white dwarf and AGB stars. So if I take again this star that I was showing at the beginning, this metal poor star, you can see here two models, and the black one is an AGB star that experienced high process, and the red one is an high process accreting white dwarf model. So the thing is that now, if you look at the heavy elements, the nucleosynthesis is very similar in these two sites. So it's very difficult to by looking just at that to say that maybe this site would be preferred than the other. The nucleosynthesis is quite similar. Maybe at some point it would be nice to check the isotopic, like to go at the isotopic level, or maybe check light elements or some other possible distinct, in order to try to make some to have some distinct signatures, between the different sites. Because if you look at the heavy elements, it's the same roughly. And this is the last, this is the last slide. I will stop after that. I think I'm going. Just a word about. I would have many things to say also, but yeah, I will stop that with just mentioning that when you have a proton ingestion, and it was shown by Iwamoto, by Cristallo, also Sergio Cristallo, if you have like a proton ingestion, you don't have only high process, you also produce a lot of lithium. And you can see here on the top right, a plot showing the surface lithium abundance of AGB stars before and after the ingestion. And this is the C12 over C13 ratio, the same kind of plot before and after. So the proton ingestion, it produces a lot of lithium and C13, and this is why the high process, at least in AGB, would come with like a low C12 over C13 ratio, and also a lot of lithium possibly. Okay, so I will stop here. So the high process is a neutron capture process that can synthesize heavy elements. One possible site, AGB stars. There is a different observational, I would say, evidence that support the existence of the high process. AGB stars can host the S and I processes. The high process develops when protons are ingested in the thermal pulse, okay. And actinides can be produced by the high process. Proton ingestion can develop up to almost solar metallicity if you include some overshoot mixing, but at high metallicity, as I mentioned, the high process signature vanishes. And there are some nuclear uncertainties which are very high for thorium and uranium. And these are a few questions that are on next steps. Of course, what is the site of the high process in the end, and their relative contribution? If there are several sites, what are their contributions? How strong is the mixing in AGB stars, the overshoot? What is the effect of rotation, magnetic field, and also need for more experimental constraints from to improve the predictive power of this nucleosynthetic synthesis model. So thank you very much for your attention, and I'll take some questions if you want.